For over a century, scientists and musicians have been locked in an argument over a single note. It is a debate centered on the difference between artistic expression and raw mechanical impact. Master pianists have always maintained that they can change the character of a note through their physical touch, subtly shifting its color from bright to dark or warm to heavy. Skeptics in the scientific community dismissed this as a psychological illusion. Their logic was simple. A performer can change the volume or the timing, but the actual texture of the sound is determined by the instrument itself. At stake is the physical reality of performance. The answer determines if the subtle variations we hear in a masterpiece are truly present in the sound waves, or if our brains are simply filling in the gaps. To understand the skepticism, look at the piano's internal machinery. The key acts as a lever that throws a felt hammer against a metal string. The problem for musicians is that the hammer actually breaks contact with the key just before it hits the string. This means that for a fraction of a second, the hammer is flying solo. The pianist has no physical way to influence it. If the speed of that hammer is the same, classical physics suggests that striking the key with a human finger, a wooden stick, or a lead brick will result in the exact same sound wave. From a purely mechanical standpoint, the idea of shaping a note through touch seemed to contradict the basic engineering of the instrument. In 2026, Dr. Shinichi Furuya and the Neuropiano Institute launched an investigation designed to look closer at this mechanical wall than ever before. They brought in 20 world-class pianists and asked them to perform a simple task: play the same notes while intentionally trying to vary the tone, moving between bright and heavy sounds. To capture what happens in that split second of impact, the team developed the HackKey, a custom non-contact sensor system that bypassed the limitations of standard high-speed cameras. This graph tracks the movement of a single keystroke at a resolution of 1,000 frames per second. It allows researchers to see the microscopic acceleration of the key in real time. For the first time, researchers had the mathematical resolution needed to determine if those invisible movements were actually happening. The sensors proved the musicians right. The data captured subtle manipulations of the key, micro-movements of the hand and finger, invisible to the human eye. These variations in acceleration, timing, and hand synchronization create measurable shifts in the piano's timbre. By changing how they approach the key, pianists actually do change the physical texture of the note. This chart shows that even listeners with no musical background consistently heard the difference between bright and dark notes. When transformed into a scatterplot, we see a direct link. Changing one physical movement predictably changed the perceived sound. This frames piano performance as an elite motor skill. The artistry we hear is the result of physical precision calibrated down to the millisecond. These discoveries are forming the basis of a new field called dynaformics, which applies the rigors of physics and neuroscience to the study of artistic expression. This shifts the foundation of music education. Instead of relying on vague instructions like play with more warmth, teachers can now show students the exact physical mechanics needed to produce a specific color of sound. In robotics, this data provides a blueprint for expressive touch. Engineers are using these human movement models to move beyond the rigid binary motions of traditional machines. The impact reaches into medical rehabilitation as well. Specialists are applying these precise motor control models to help stroke victims regain the intricate hand coordination required for daily life. Solving this 100-year-old mystery confirms that the most subtle human actions can have a physical power that is both measurable and audible to the world.